Good morning, everyone. So, in the last class, we introduced the concept of matrix transformation, which was defined a map from Rn to Rm. Now, instead of Rn to Rm, now we are interested the generalization of matrix transformation, which is linear transformation, which is a map which is defined from V to W. So we say that let V and W are vector spaces, then a map from V to W is a linear map or a linear transformation if it satisfies the following two properties. Recall that here addition means vector addition. So on the left hand side there is a vector addition between the vectors of V, while on the right hand side the vector addition is for the vectors of W. Similarly, for the second property, there is scalar multiplication k dot u, and on the right hand side, there is scalar multiplication between a scalar and a vector of w. If the following two properties holds, then we say it is a linear transformation. If both the vector spaces are same, then we say T is a operator. So this one is straightforward. We discussed in the last class also. If I take the left hand side, or if I just take T of k1 v1 plus T of k2 v2, then from the first property I can write it like T of k1 v1 plus T of k2 v2, and then from the second property I can write k1 T of v1 plus k2 T of v2. Similarly, I can generalize it. So if T is a linear transformation, then T of k1 v1 plus so on kn vn is same as k1 T of v1 and so on. So let V and W be the two vector spaces. Then you need to tell me, recall the zero transformation. Is it a linear transformation? So zero transformation is a transformation which takes every vector to the zero vector. Yes, so if I write the left hand side T of u plus v, it must be the zero vector, and T of u plus T of v is 0 plus 0, which is the zero vector. So left hand side is equal to right hand side. Similarly, if I see the second property T of k dot u, so k dot u is a vector and therefore it is a zero vector, and k dot T of u becomes k dot zero vector of w, which again becomes the zero vector. So both the properties are satisfied and therefore it is a linear transformation. Similarly, recall the identity operator and check if it is a linear transformation. This one is again straightforward because identity operator is defined as follows. It takes every vector u to u and therefore it is defined from v to v. So T of u plus v becomes u plus v, which is same as T of u plus T of v. And similarly, we can show the second property holds. Let's move to the next question. L is a map from M matrix set of the matrix of vector spaces Mn to vector space Mnm, such that L of A is equal to A transpose. Check if L is a linear transformation. This one is again very simple. I am just showing you the method that how do we write it. So you always start by taking two vectors in V. So here it is Mn, and then the left hand side says that T of A plus B should be equal to, or L of A plus B should be equal to L of A plus L of B, which is A plus B transpose. Now A plus B transpose, so recall the properties of a transpose. This can be written as A transpose plus B transpose. A transpose becomes L of A plus B transpose becomes L of B. So first property hold. Similarly, we can show that the second property holds as follows, and therefore it is a linear transformation. This is again interesting in a simple result. It says that if T is a linear transformation, then T of 0 should be equal to the 0 vector, which means If it is a linear transformation, then the 0 vector must be mapped to the 0 vector, or 0 vector of v must be mapped to the 0 vector of w. It also means that if t of 0 is not equal to the 0 vector, then t is not a linear transformation. The proof is very easy. If you recall, t of k dot u is equal to k t of u. So if you take k is equal to 0, then t of 0 dot u is equal to 0 dot t of u. T of 0 dot u becomes the 0 vector of v, and 0 dot a vector of w becomes the 0 vector of w. We did this property already related to the vector spaces. Similarly, using the property that t of u plus minus v, which is t of u plus t of minus v, you can write it as t of u minus t of v. So both are easy to prove. Let's see a question. It says that determine whether it is a linear transformation. So if you try it by yourself, it is easy to prove that one of the two properties does not hold. But what I want to show here is that zero vector is not mapped to the 0 vector. So v and w are p2 only, so its 0 vector is 0 plus 0x plus 0x square. Now if you compute t of 0 plus 0x plus 0x square, it should be equal to 0 plus 0x plus 0x square using this property. But now if you see it, it is coming out to be a is equal to 0, so 1 plus x square, which is not equal to 0 plus 0x plus 0x square, and therefore t is not a linear transformation. Yes. Now check whether the following are linear transformations. Please do each one by one. I am going to discuss few of them. So I will start with the first one, p2 to r cube. So again I have to take two vectors u and v in p2. They looks like u is equal to a1 plus b1x plus c1x square, and v is a2 plus b2x plus c2x square. So t of u plus v, which means you add the following two polynomial, which becomes a1 plus a2 plus b1 plus b2x plus c1 plus c2 x square. And now it is given that t of a plus bx plus cx square is equal to abc. It means that t of this becomes a1 plus a2 b1 plus b2 c1 plus c2. I can write it as a1 b1 c1 plus a2 b2 c2, and therefore it becomes t of u plus t of v. Similarly, it is easy to show the second property holds, and therefore it is a linear transformation. T of ku becomes t of ka1 plus kb1x plus kc1x square, which is equal to ka1 kb1 kc1, which is k times a1 b1 c1, which is k t of u, and therefore it is a linear transformation. If we see the second one, it is from Pn to Pn plus 1. T of Px is x time Px. So again, if I take P and Q belongs to Pn, then T of P plus Q becomes x times P plus Q, which is same as x time P of x plus x time Q of x, and which becomes T of P plus T of Q. Similarly, the second property is very easy to show, and therefore it is a linear transformation. So this becomes kp of x, kxp of x, and therefore it becomes k times t of p. Okay, t of x is equal to sine x. Again I take xy in R, and that gives me t of x plus y is sine x plus y. Now if I compute t of x plus t of y, it is sine x plus sine y. So you can see that the left hand side is not equal to right hand side. You just need to identify the values of x and y, because for some values it may be equal. So you just need to identify those values of x and y for which it is not equal. For example, for x is equal to pi by 2 and y is equal to pi by 2, my left hand side is sine pi, which is 0, and right hand side is sine pi by 2 plus sine pi by 2, which is 2. So therefore it is not a linear transformation. Again, if I take t of x plus y, so left hand side is x plus y square, and the right hand side is x square plus y square. Again, if you choose x is equal to 1, y is equal to 2, left hand side is 2 plus 3, which is 9, and right hand side is 1 square plus 2 square, which is 5. They are unequal, and therefore it is not a linear transformation. Next one is you are multiplying the diagonal entries. Again, it's easy to see how you write t of a plus b and t of a plus t of b. So t of a plus t of b is a11, a22, ann plus on this side b11, b22, bnn, and t of a plus b is actually a11 plus b11, a22 plus b22, and so on. Again, left hand side cannot be equal to the right hand side. Take any example of m22, something like this, and you can easily produce the counter example. So not a linear transformation. This one is interesting and easy to prove. So again I will give you a counter example. Let us consider a is 1001, b is also 1001. So t of a plus t of b is rank a plus rank b. Both have the rank 2 and therefore it is 4. Now t of a plus b is rank of the matrix 2002, which is equal to 2. So t of a plus b is not equal to ta plus tb, and therefore it is not a linear transformation. So let's move to the next question, which says that let t be a linear operator, and we have not given the linear transformation. We just have given t of 100, t of 010, and t of 001. We need to find t of minus 324. Question is easy, just we need to use the property of the linear transformation. So here it's interesting to observe that 100, 010, and 001 are the basis vectors of R cube, and therefore minus 324 can be expressed as minus 3100 plus 2 times 010 plus 4 times 001, and if we apply t on both the side, it becomes t of minus 324 is minus 3 times t100, which is given, plus 2 times t of 010 plus 4 times 001. If you substitute the values and solve it, then you will get the required answer. And the same approach can be used to compute t of xyz. So please do remember this question, because here the linear transformation is not given explicitly, it is given implicitly, and using the given information we computed t of x, y, z, which is as follows. Even this is what we did in the previous question, that if S is a basis for V, then any vector V can be expressed as a linear combination of basis vectors, and then we apply T on both the sides, which gives us T of V as a linear combination of T of V1, T of V2 and T of Vn. This is a similar question, please do try by yourself. Solution has already been added to the slides. This is an interesting question. It's not difficult, but I just want to show that when we talk about the linear transformation, it's not always the operations are usual addition and scalar multiplication. So in this case, the operations are different, and t of xy is 2 dot xy. So t of xy is 2 dot xy. I am not solving in detail, but what need to be done is you have to see left hand side should be equal to right hand side. If I start with left hand side, so it's something like t of x1 y1 plus x2 y2, which is t of x1 plus x2 y1 plus y2, which becomes 2 dot x1 plus x2 y1 plus y2. And now we have to use the given information, so this becomes 2x1 plus 2x2 plus 2 minus 1, which is 1. The next one is 2y1 plus 2y2 minus 4 plus 2, which is minus 2. Similarly, you must compute the right hand side, which is t of x1 y1 plus t of x2 y2. Now this plus is important. Even yes, I did a mistake, because here this plus is defined not as the usual one. I have to follow the information which is given. So t of x1 y1 plus x2 y2 is x1 plus x2 plus 1 and y1 plus y2 minus 2, and then it is 2 times x1 plus x2 plus 1 y1 plus y2 minus 2, and then it becomes 2x1 plus 2x2 plus 2, then plus 2 minus 1, which is plus 3, and similarly 2y1 plus 2y2 minus 4 plus 2, which is minus 6. This is my left hand side. Similarly, if I compute the right hand side, they must comes out to be equal, but this is a little bit tricky. You need to be very careful. There are high chances that you do a very small mistake, but I am telling you that it is a linear transformation, so please do solve by yourself. This is a question which is for an exercise, very easy to solve. Please do it. And in the next class, we want to move towards the process to show that under what condition two vector spaces are isomorphic. And for that, we need to show that the given linear transformation is 1, 1 and on 2. Thank you very much.